Hello viewers. In this video, I am going to illustrate about some numerical problems on high performance liquid chromatography, gas chromatography, ion exchange chromatography, and thin layer chromatography. Let us have the first problem. The problem states like this. The acetaminophen content of tablet is determined by HPLC using acetylsilane column and 38:62 methanol and water as mobile phase. The UV detection is set at 254 nanometer. A 10 microliter standard solution containing 12 ppm acetaminophen is eluted out with response from the detector as 0.324 arbitrary units. 10 tablets are ground into fine powder and their extract prepared into 500 ml. A 1 ml of extract is diluted to 25 ml with the mobile phase, and a 10 microliter is injected into the column. The resulted absorption is 0.232 arbitrary units. What weight of acetaminophen is present in each tablet? So this is the problem stated. So in this problem, the objective is to determine the acetaminophen content in one tablet. So there is a brand of tablet was given for analysis by high performance liquid chromatographic technique, which was eluted at certain retention time. And by using the signal given by the detector, UV absorption detector was used, which was set at 254 nanometer. So what was the concentration? You have to determine first. You have to determine what is the amount of acetaminophen present in each tablet. You have to report. This problem looks very simple. So we know any instrumental technique you take, whatever the response given by the instrument, its signal will be directly proportional to concentration. That's what is given. Concentration is proportional to signal, or concentration is also equal to K into S, where K is the proportionality constant. So you can use this expression and you can calculate what is the amount of the solute or the concentration of the solute available in the unknown can be determined. In order to do this, first we have to obtain the value of K, where K is the proportionality constant. For each and every instrumental technique, since the concentration is proportional to the signal, what is the proportionality constant? It should be known. So it has to be determined whether it may be HPLC or cyclic voltammetry or differential pulse voltammetry or something else. So whatever the instrumental technique you are following. So let us start this. So what is given? HPLC was used for eluting acetaminophen. Acetaminophen was present in standard as well as the sample. So what was the concentration of acetaminophen in standard? It was 12 ppm. What is the signal given by the detector for the standard, 12 ppm standard? It is 0.324 arbitrary units. So then the sample was introduced. The signal given by the instrument is 0.234 arbitrary units. What is the concentration with respect to this 0.232 arbitrary units that you have to determine? So you know the concentration of the standard and the signal. So first you calculate the proportionality constant. So K is equal to concentration is 12 ppm. So 12 divided by the signal is 0.324. That is going to be 37.04. The value of K is 37.04. Okay, then for sample, now you know the value of K. What is the concentration of acetaminophen in the sample? You can determine. So C is equal to K into S. K, you know, signal, you know, that is 0.232 arbitrary units. You just substitute. C is equal to 37.04 into 0.232. So that gives you 8.59 ppm. So 8.59 ppm of acetaminophen is present. This is what the concentration of acetaminophen in the 10 microliter of the standard solution, which is containing 12 ppm acetaminophen, which is injected into the chromatographic column. That you have to report. So 8.59 ppm of the solute is present in 10 microliter of 1:25 extract, 1:25 times diluted extract. How this is? Here 1 ml of extract is diluted to 25 ml with a mobile phase, out of which only 10 microliter is injected. Okay. So You have to calculate weight of acetaminophen in 10 tablets extract because 10 tablets were grinded and prepared the sample solution. Here, 10 tablets were grinded and prepared the sample solution, which was taken in 1 ml and diluted to 25 ml, out of which 10 microliter was injected. What was the total volume of tablet extract prepared? 500 ml. This 500 ml was having 10 tablets. Okay, all right. So weight of acetaminophen in 10 tablets extract is equal to 8.59 ppm means 8.59 milligram per liter. Liter means 1000 ml. So 8.59 ppm I have written just as 8.59 milligram per 1 liter, that is 1000 ml into 25 ml, because only 25 ml volume was prepared by using 1 ml from this 500 ml. The dilution was made up to 25 ml. So what is the amount of acetaminophen or the milligrams of acetaminophen present in 25 ml? So 8.59 milligram in 1000 ml. So in 25 ml, 8.59 divided by 1000 into 25. Okay, then only 1 ml extract was taken. So this gives you the amount of acetaminophen present in diluted 25 ml. Diluted 25 ml of the tablet extract. So, it is also equivalent to 1 ml of the tablet extract taken from the original tablet extract. It is undiluted. It is not diluted. From 500 ml, 1 ml was taken. So, in 1 ml, this much of acetaminophen is present. So, in 500 ml, how much is present? You substitute. So, 8.59 milligram divided by 1000 ml into 25 divided by 1 into 500. So you will get 107.38 milligrams. This 107.38 milligram of acetaminophen is present in 500 ml, or it is contained with 10 tablets. So what is the weight of acetaminophen present in 1 tablet? So acetaminophen present in 10 tablets divided by 10. So 107.38 milligram divided by 10, you will get 10.738 milligram. This is the final answer. So this is how we can solve. This equation is very important for any instrumental technique, whether the signal may be current or voltage or area or number of theoretical plates or arbitrary absorbance units, whatever it is. C is proportional to the signal. So by using this expression, we can calculate the concentration of the analyte present in any sample. This is how we can solve these type of problems. I hope you have understood this. Let us go to the next one. This is very similar to the previous one, but the real sample taken was different than the previous one. The concentration of polyaromatic hydrocarbons, that is denoted by PAH, in soil is extracted and subjected to analysis by HPLC-UV technique. In a typical analysis, a 2.013 gram sample of dried soil is extracted with 20 ml of methylene chloride. After filtering, 1 ml portion of the extract is removed and diluted extract into an HPLC gives a signal of 0.217 arbitrary units for PAH fluoranthene. When 5 microliter of a 20 ppm fluoranthene standard is analyzed in the same conditions, a signal of 0.258 is measured. Report the ppm of fluoranthene in the soil. This is the problem. So same equation holds good. C is equal to K into S. First, you should know the concentration of the standard and the arbitrary units are the signal by the detector for the standard. That is given here. 5 microliter of 20 ppm fluoranthene was injected into the column. It has given 0.258 arbitrary units as the detector signal. You know, this is the detector signal for the standard. This is the concentration of the standard. So you just substitute. K is equal to concentration of the standard divided by the detector signal. You will get 77.52. Concentration of the standard is 20 ppm and the detector signal for the standard is 0.258 arbitrary units. So K is equal to 20 by 0.258. That gives you 77.52. Okay, now the determination of the proportionality constant is over. Next, let us move on to the sample. What sample has been taken? The soil sample was containing polyaromatic hydrocarbon because of a spraying of variety of the pesticides onto the plants. soil is polluted with these polyaromatic hydrocarbons. Therefore, analysis of the soil is very significant. So concentration of fluoranthene in soil you have to determine. In soil extract you have to determine. First, soil has been taken and extracted into methylene chloride. After filtering the soil extract, 1 ml portion was diluted. The diluted volume has not been given. So directly you can determine what is the amount of fluoranthene available in this 1 ml. So the signal given by the instrument is 0.217 arbitrary units, and the K value is 77.52. Calculate the value of C, concentration of fluoranthene, is equal to K into S, that is 77.52 into 0.217. That gives you 16.82 ppm. So this is the concentration of fluoranthene with respect to the signal given by the instrument. Next, the final step is what ppm of fluoranthene present in the soil. What ppm of fluoranthene is present in the soil. So the soil is extracted to 20 ml because 20 ml of methylene chloride was used. So 16.82 ppm means 16.82 milligram per liter, that is 1000 ml. So how much in 20 ml? So that is equal to 16.82 milligram per 1000 ml into 20 ml. So this is the amount of fluoranthene available in 2.013 gram of soil, because 2.013 gram of soil was extracted and prepared 20 ml extract. Therefore, in 1 gram of soil, how much fluoranthene is present? So ppm for solids means milligram per gram. So in 2.013 gram of soil, this much amount of fluoranthene is present. So in 1 gram of soil, how much is present? You just substitute. 16.82 is obtained by the previous equation, divided by 1000 ml into 20 divided by weight of soil into 1 gram. That gives you 0.1671. This is the milligram of fluoranthene available in 1 gram of soil, which has been polluted by the polyaromatic hydrocarbon. So this looks very simple. So this problem can be solved by using the equation C is equal to K into S, or C is proportional to S. This is how we can solve this type of problems. So let us go to the next one. This is in connection to gas chromatography. It was used to determine chloroform content in drinking water. So in the analysis of chloroform in drinking water by gas chromatography, a single standard containing 1.3 ppb parts per billion, 1.3 ppb gives a peak area of 1.35 into 10 power 4. If analysis of water from drinking water fountain gives a peak area of 1.56 into 10 power 4, what is the concentration of chloroform in the sample? This is the problem. So here also, standard chloroform was taken and it was injected into the gas chromatographic column, and the signal obtained by the instrument has been noted, that is 1.35 into 10 power 4. The concentration of the standard was 1.3 ppb. Calculate the value of K. So K can be calculated as C is 1.3 ppb divided by the detector signal is 1.35 into 10 power 4. So the value of K is 9.63 into 10 power minus 5. Then next, go to analysis of sample. Water sample from a drinking water fountain was taken and it was injected into the gas chromatography column. The signal given by the instrument is 1.56 into 10 power 4. So concentration in the fountain water is equal to C, which is equal to K. The value of K is 9.63 into 10 power minus 5 into the signal given by the instrument. So that is going to give you 1.502 ppb. Right? So this is how very simple problem this is. Only thing is you have to use the equation C is equal to K into S, where K is the proportionality constant with respect to instrumental techniques that can be determined by using the concentration of the standard and the signal given by the instrument for the standard. Similar problem has been given here, but instead of chloroform, it is phenol content. Trace amounts of phenol in water can be detected by HPLC. If a 50 nanogram phenol standard gives a peak area of 140 units and a 20 microliter water sample gives a peak area due to phenol of 26 units, calculate the phenol content as parts per million. what is the concentration of phenol in water? You have to report in parts per million. So standard phenol of 50 nanogram was introduced to the HPLC column. The signal given by the instrument is 140 units. So K is equal to concentration is 50 nanograms and the instrument signal is 140 units. So the value of K is 0.3571. A 20 microliter sample was introduced and the instrument signal is 26 units. What is the concentration? What is the concentration? So calculate the phenol content as parts per million. You have to determine. So if you determine that, you will get 9.29 nanogram. 9.29 nanogram. So how do you get this 9.29? C is equal to K into S. So K is 0.3571. So concentration of phenol in water is equal to 0.3571 into 26. So you will get 9.29 nanograms. 9.29 nanograms of phenol is present in the water sample. Water sample. What was the volume injected? 20 microliter. So they are asking to report in parts per million. So you have to determine the milligram of phenol present in 1 liter of water. So 9.29 nanogram, which is present in 20 microliter, that is 20 into 10 power minus 6 liter. So how much is present in 1 liter? How much is present in 1 liter? So 9.29 nanogram divided by 20 microliter, that is 20 into 10 power minus 6 liter into 1 liter, which is going to be 464500 nanogram per liter. You convert this into milligram per liter. 464500 into nanogram means 10 power minus 9 gram. 10 power minus 9 means 10 power minus 6 into 10 power minus 3. So gram per liter will be remained as such. So 464500 into 10 power minus 6 milligram per liter. That is going to be the answer. So if you multiply this 464500 with 10 power minus 6, you will get 0.4645. So milligram per liter, 10 power minus 3 gram per liter means it is ppm. So 0.4645 ppm will be the final answer. So this is how you can solve this type of problems. Okay, let us move on to other problem. This problem, what is displayed here, is related to ion exchange chromatography to determine ion exchange capacity. Ion exchange capacity is a very important parameter to express the extent of degree of cross-linking for ion exchange resins, cation exchange resin and anion exchange resin. Both have been illustrated here. So let us go one by one. In the first problem, you concentrate on the left half. The sodium ion in 200 ml of a solution containing 10 gram per liter NaCl is to be removed by passing through a cation exchange column in the hydrogen form. If the ion exchange capacity of the resin is 5.1 milliequivalents per gram of dry resin, what is the minimum weight of dry resin required? So in the column, cation exchange resin was taken, which was in the hydrogen form, which is suitable for the separation of cations. That's what it is, cation exchange chromatography. What is the ion exchange capacity of cation exchange resin? You have to determine. So how to determine the ion exchange capacity? That is done by eluting sodium chloride through cation exchange resin, which is in the hydrogen form. The effluent, which is containing hydrogen ion, can be titrated with sodium hydroxide. Sodium hydroxide. And ion exchange capacity can be calculated by using IEC is equal to AV divided by W, where A is the concentration of Na plus, V is the volume, and W is the weight of the resin. Okay. So A is concentration of Na plus, V is the volume of Na plus, W is the weight of the resin. Given that the ion exchange capacity is given, that is 5.1 milliequivalents per gram, we have to calculate what is the minimum weight of the resin, that is W we have to calculate. Right. So weight of NaCl passed through the column is 10 gram per 1 liter. 10 gram per 1 liter. So 10 gram of sodium chloride was dissolved in water and prepared 1 liter solution, out of which 20 ml has been passed through the column. 200 ml of the solution has been passed through the column. So 10 gram of NaCl in 1 liter. 10 gram of NaCl in 1 liter. Therefore, in 200 ml solution, 10 gram per 1 liter or 1000 milligram are there. In 200 milligram, how much NaCl is present? So that is 10 divided by 1000 into 200. That gives you 2 gram of NaCl. So this 200 ml of a solution containing 2 gram of NaCl. So this 2 gram of NaCl in 200 ml will give you 0.1711 molar. The concentration of Na plus in this 200 ml solution is 0.1711 mole per liter or molar. Therefore, use this expression W is equal to A into V divided by IEC. W is equal to A means the concentration of Na plus, that is 0.1711 mole per liter, into volume is 200 ml divided by ion exchange capacity is 5.1. So that gives you 6.71 gram. 6.71 gram. So we require 6.71 gram of cation exchange resin to elute sodium ion comfortably after passing 200 ml solution. So this is how. So IEC, ion exchange capacity, can be calculated by using the expression IEC is equal to A into V divided by W. Because A and V are given, IEC has also been given, W we have to calculate. This is for cation exchange resin. This is related to anion exchange resin. Here, you have to calculate the ion exchange capacity of the anion exchange resin. What is the problem? The problem is stated like this. A 0.5 gram of dried anion exchange resin was filled into burette, washed thoroughly with double distilled water, and passed a 250 ml solution of 0.25 molar NaNO3 at a flow rate of 2 ml per minute. The effluent collected and titrated with 12.9 ml of 0.02 molar AgNO3 solution to the potassium chromate indicator's endpoint. What is the ion exchange capacity of the resin? Very simple. So this problem was stating and making you to understand how to calculate the ion exchange capacity of anion exchange resin. A column has been filled with the 0.5 gram of dried anion exchange resin, and it was washed with 250 ml solution of 0.25 molar sodium nitrate solution. Because this is anion exchange resin, all the anions such as NO3 minus will be replaced in place of chloride ion, because anion exchange resin will be in the chloride form. All the chlorides are eluted. So the effluent containing the chloride ions. The chloride ions present in effluent can be titrated with AgNO3 by Morse method using potassium chromate indicators method. This is going to be precipitation titration. So what was the volume of silver nitrate consumed? 12.9 ml. The concentration of silver nitrate is given, that is 0.02 molar. So directly you can substitute and calculate the ion exchange capacity. So concentration of AgNO3 is known, volume of AgNO3 is known, weight of resin is 0.5 gram. Calculate IEC. So IEC is equal to 12.9 ml into 0.02 moles per liter of AgNO3 divided by 0.5 gram of resin. So 0.516 milliequivalents per gram. This is going to be the equivalent ion exchange capacity of anion exchange resin in order to elute the chloride from the anion exchange column. Okay, I hope you have understood. These two problems are different in nature, but both are related to ion exchange capacity. Next one. A cation exchange chromatography column containing 0.1 gram dried resin was washed with a 50 ml of NaCl, and the effluent was titrated with 10.9 ml of 0.015 molar MeOH to methyl orange endpoint. What is the ion exchange capacity of resin? This problem is related to cation exchange resin. This is related to anion exchange resin. So here, 0.1 gram of dried cation exchange resin was taken, and it was washed with 50 ml of NaCl. What happens when you wash the column with 50 ml NaCl? All hydrogen ions are going to be exchanged by sodium ion. So the effluent is containing hydrogen ion. That hydrogen ions present in effluent was titrated with NaOH. What was the volume consumed? 10.9 ml. and the concentration is 0.015 molar. Substitute. Ion exchange capacity is equal to volume of NaOH consumed into concentration of NaOH divided by weight of cation exchange resin. Weight is 0.1 gram. So ion exchange capacity is volume of NaOH is 10.9 ml. Concentration of NaOH is 0.015 molar and weight is 0.1 gram. Substitute. So ion exchange capacity is 10.9 into 0.015 divided by 0.1. So you will get 1.635 milliequivalents per gram. So this is the relative equivalent ion exchange capacity of cation exchange resin. So this is about calculation of the ion exchange capacity or the weight of ion exchange resin, which is possessing some specific ion exchange capacity in order to do the separation by ion exchange process. Okay, so this is related to application of ion exchange chromatography to determine total cation concentration. So very interesting here. You look at the problem. Ion exchange chromatography is employed to analyze wastewater for total cation concentration. This you have studied as one of the applications of ion exchange chromatography. A 50 ml of wastewater sample has total alkalinity of 234 ppm calcium carbonate. Is passed through cation exchange column containing H plus form of resin, that is ReSO3 minus H plus. And the effluent is titrated with 23.4 ml of 0.025 mole per liter NaOH to phenolphthalein endpoint. What is the total cation concentration of water sample in ppm calcium carbonate? So total cation concentration means it is the summation of the alkalinity of water sample and equivalent mineral acidity. Equivalent mineral acidity means if you pass a water sample through the cation exchange resin, all the hydrogen ions are going to be exchanged by the cations which are present in water sample. So the effluent eluted out with hydrogen ion can be titrated with NaOH. If you calculate the acidity, that is equivalent mineral acidity. How the acidity will be calculated? So if you multiply the volume of NaOH consumed, concentration of NaOH with 50, that is the equivalent mass of calcium carbonate, you will get acidity of wastewater. That is nothing but equivalent mineral acidity. And alkalinity, they have given directly, you need not to calculate. The alkalinity of water is 234 ppm. This 234 ppm alkalinity means whenever a cation exchange resin which is having hydrogen ion, the resin is in the hydrogen ion form, is treated or passed with water sample having say carbonates, bicarbonates, hydroxides, along with some metals, alkali metals. So all the metals or alkali metals are going to be exchanged, and the hydrogen ion will be released to the effluent. So the effluent is having H plus ion and reacted with carbonate or hydroxide or bicarbonate. All these bases are neutralized. So to what extent these bases are present? 234 ppm. 234 ppm. So they have directly given. So first you calculate the equivalent mineral acidity, then add that with alkalinity, you will get total cation concentration. So equivalent mineral acidity is concentration and volume of NaOH into 50 into 1000 divided by volume of the sample. So you have to express the result in ppm calcium carbonate. So you have to convert the milligram of the acidic species present in 1 liter. So V is the volume of the sample. That is how much? 50 ml water sample is passed. So V is 50. So 23.4 ml NaOH was consumed of concentration 0.025 molar into 50 into 1000 divided by 50. In 50 ml, this much amount of calcium carbonate is present. That is equivalent to equivalent mineral acidity. So in 1000 ml, how much is present? So 585 milligram per liter or 585 ppm. So equivalent mineral acidity is 585 ppm. Therefore, the total cation concentration is alkalinity, that is 234, and equivalent mineral acidity, that is 585 ppm. So you will get 819 ppm calcium carbonate. So this is how this problem will illustrate the application of ion exchange chromatography to determine the acidity as well as equivalent mineral acidity along with total cation concentration. So not only this, any species, if they are present in the cationic form, they can be used to determine their concentration. So you take the water sample, you just pass through the column containing cation exchange region, and you can determine. Okay, let us move on to the next problem. This is related to TLC. In TLC, very importantly, you have to determine either retardation factor, a retention factor, or distance moved by the solute. These are all the things you can determine in TLC. So first problem, you can understand by looking at this problem, what you have to determine. Okay, a sample containing 3 amino acids, namely glycine, alanine, and methionine, is spotted on the marked line on TLC plate and placed in TLC chamber containing 45:25:30 mixture of chloroform, benzyl alcohol, and acetic acid as mobile phase. The solvent is traveled by a distance of 16 centimeter from sample introduction line of TLC plate. The calculated retardation factors for glycine, alanine, and methionine are 0.24, 0.32, and 0.46 respectively. Find out the distance in centimeter migrated by each amino acid on TLC plate from the origin of the sample spot. Calculate the retention factors for each compound. So 3 amino acids, namely glycine, alanine, and methionine, were taken, and they were spotted on TLC plate. Using the distance traveled by these amino acids, the RF values were calculated. The calculated RF values were given as 0.24, 0.32, and 0.46. They have been tabulated here. And the mobile phase, which is a mixture of chloroform, benzyl alcohol, and acetic acid, which has showed the movement of 16 centimeter. So that is dm. The distance moved by the mobile phase is dm. Right. You know the relationship that RF is equal to dr by dm. RF is equal to dr by dm. So what they're asking, you have to calculate the retention factors and the distance moved by each amino acid you have to determine. So we know RF is equal to dr by dm. So dr is equal to RF into dm. RF values have been given. For glycine, it is 0.24. For alanine, it is 0.32. For methionine, it is 0.46. dm value is given. 16 centimeter has been moved by the mobile phase. Simply calculate the dr. dr is equal to 0.24 into 16. You will get 3.84 centimeter. Similarly, for alanine, 0.32 into 16, you will get 5.12 centimeter. For methionine, RF is 0.46, dm is 16. So 0.46 into 7.16 centimeter, you will get 7.36 centimeter. These are the distances moved by glycine, alanine, and methionine respectively. Then the next part is you have to calculate the retention factors for each compound. Retention factor in TLC is also denoted by small k. RF is the retardation factor. Don't be confused. RF is the retardation factor. Small k or k dash is the retention factor or capacity factor. That is calculated by using the expression 1 minus RF divided by RF. 1 minus RF divided by RF. So RF value is known for each and every amino acid. You just substitute and calculate the value of capacity factor. So for glycine, K is equal to 1 minus 0.24 divided by 0.24. You will get 3.167. For alanine, 1 minus 0.32 divided by 0.32. You will get this answer. For methionine, 1 minus 0.46 divided by 0.46. You will get 1.174. So this is how you can calculate the retention factor or the retardation factor. If the distance moved by the solutes and the mobile phase given, you can calculate the RF, and in turn you can calculate the capacity factor. So this is how the TLC related problems can be illustrated. Another interesting problem here. Use the following data of TLC separation and calculate the values of RF and K for solutes A, B, and C. Instead of glycine, alanine, and methionine, it is just given as solute A, solute B, and solute C. TLC stationary phase used was bonded silica. Mobile phase was mixture of chloroform, benzyl alcohol, and acetic acid. So solute A has moved a distance of 9.12 centimeter. Solute B has moved a distance of 6.34 centimeter. Solute C has moved a distance of 3.11 centimeter. Whereas the mobile phase has moved the longer distance, that is 14 centimeter. So you have to calculate the RF value. What is RF? dr divided by dm. dm is the distance moved by the mobile phase. dm is the distance moved by the mobile phase. So these three values are dr for solute A, solute B, and solute C. This is going to be dm. You just substitute. So RF is equal to dr divided by dm. So dr is 9.12 for solute A, dm is 14. So 9.12 divided by 14, that is 0.65. For solute B, the distance dr is 6.34 and dm is 14. So 6.34 divided by 14, you will get 0.45. For solute C, it is 3.11 divided by 14, you will get 0.22. So RF is ready now. RF is ready. Calculate the value of K. What is K? Capacity factor or retention factor. It can be calculated as illustrated in the previous problem. 1 minus RF divided by RF. So RF value is known. Calculate the K value for solute A, solute B, and solute C. So 1 minus 0.65, that is 0.54. 1 minus 0.45 divided by 0.45, 1.22. 1 minus 0.22 divided by 0.22, 3.55. So this is how. So K is equal to 1 minus RF divided by RF. For this compound, solute A, 1 minus 0.65 divided by 0.65, you will get 0.54. For solute B, 1 minus 0.45 divided by 0.45, you will get 1.22. For solute C, you will get K value after substituting the RF value in the equation 1 minus RF divided by RF, that is 1 minus 0.22 divided by 0.22, that is 3.55. So like this, when you are trying to solve the numerical problems, you can understand the theory involved in separation by TLC very well. So this is all about some numerical problems related to TLC.